Heterogeneous equilibria, which is result from the reversible reactions involving the ethane and products are in a different phase. For example, when the calcium carbonate is hit in the closed vessel, which is calcium carbonate in the solid phase, and then the products in the solid and gas phase, which is two solid and one gas, constitute three separate phases at the equilibrium. So Kc primes is equal to the concentrations of the product CaO and CO2 divided by the concentration of the reactant CaCO3. So remember again that Kc primes here is to distinguish from the final form of the equilibrium constant to be derived shortly. The concentration of solid, like its density, is an intrinsic property which does not depends on the substance presence. For example, the molar concentration of the copper, given that the density is equal to 8.96 gram per cm cube, which is the concentration is same whether we have 1 gram or 1 ton of metal. So from the density, we can convert into the molar mass or molarity by multiplying with the molar mass of the cuprums. So for this reason, the term concentrations of the calcium carbonate and calcium oxides are constant and combined with the equilibrium constant. So the solid phase times to the Kc primes is equal to the Kc finals and equal to the concentrations of the carbon dioxide. So the new Kc is equal to the concentrations of the carbon dioxide. Okay, let me try solve this equation, which is write equilibrium constant expression Kc and Kp. Okay, for A, which is Kc prime is equal to NH3 Okay, since that this is in solid phase, so we can write the Kc is equal to NH3 Alternatively, we can also express the equilibrium constant in Kp since this is in gas phase. So Kp is equal to P2NH3 PH2SA. Okay, for B, Kc prime is equal to Ag plus so Kc is equal to Ag plus Cl minus, since this is also in solid. And for C, which is Kc prime is equal to PCl3 so Kc is equal to 1 over Cl2, or we can also express in Kp since chlorine in gas. Cl2. Okay. Okay, consider the following heterogeneous equilibriums at 800 degrees Celsius, which is the pressure of carbon dioxide is equal to 0.236 atm. So calculate the Kp and Kc. Since from these equations, only CO2 is in gas phase, so Kp is equal to PCO2 equal to 0.236 atm. So from that we want to calculate the Kc. From the equation, Kp is equal to Kc 0.0821 and change in N. Okay, from this equation we can see that the change in N is equal to 1, okay, which is only 1 mole gas. reagents. So we substitute into this equation 0.236 Kc times to 0.0821. So we get Kc is equal to 2.6x times 10 power negative 3. Multiple equilibria is more complicated situation, which is one in which the products or molecule in one equilibrium system are involved in a second equilibrium process. Okay, for example, the reaction between A and B producing C and D, then C and D producing E and F, which is the product formed in the first reaction, which is C and D, react further to form a product E and F. So at equilibrium, we can write two separate equilibrium constant, which is Kc prime for the first reactions. The concentration of the products C and D divided by the concentration of the reactants, and Kc prime double prime, which is equal to the concentration of the product EF divided by the concentrations of the reactant CD. So the overall reaction is given by the summations of the two reactions, okay, from the reaction 1 and reaction 2. So the overall reaction is equal to AB producing E and F. So C and D we can cancel here, and the equilibrium constant for the final or the overall reaction is equal to Kc, concentration of E and F divided by the concentration of AB. Otherwise, we can also obtain the same expressions if we take the product of expression for Kc prime and Kc double primes, which is Kc prime times to Kc double primes to get the final Kc. So Kc is equal to Kc prime multiplied by Kc double prime. So if the reaction can be expressed as the sum of two or more reactions, so the equilibrium constant for the overall reactions is given by the product of the equilibrium constant of the individual reactions. For example, we have a diprotic acid H2O, which has 2 mole of hydrogen here. So when it dissolves in water, it can the mixture will contain H2A, HA, and A2 minus. For example, H2A dissolve, so we can get HA and H plus. So K1 is equal to concentration of the HA and we also has these equations. K2 is equal to concentration of A2 and HA. So the final concentration of Kc is equal to for example, the dissociation of the acetic acid, okay, H3CO3 H plus. So Kc prime is equal to concentration of products. Sorry. And then this one Kc double primes is equal to HCO3. So the overall reaction is the sum of these two equations. So we can delete here. So we can get H2CO3 producing, okay, 1 plus 1 equal to 2 and CO3. So from the summations of the two equations, we can calculate the final equilibrium constant. Kc is equal to Kc prime times to Kc double primes. So we can get the final value Kc. The form of K and equilibrium equations for conditions 1. When the equation for a reversible reaction is written in the opposite directions, so the equilibrium constant becomes the reciprocals of the original equilibrium constants. Okay, consider these equations. Okay, which is Kc is equal to concentrations of the NO2 okay, which is the value is equal to 4.63 times 10 or negative 3. Okay, when the reaction is reversed, so means that the Kc primes is equal to 1 Kc or equal to 1 over or divide by 4.63 times 10 power negative 3, so we get 216, which is k times to k1 is equal to 1. So we need to specify how the equilibrium equation is right. So we can write kc is equal to 1 over kc primes, or k times to kc primes is equal to 1. Okay, the value of K also depends on how the equilibrium equations is balanced. So from these equations, the Kc prime is equal to concentration of NO2 divided by N2O4. While for this one, Kc is equal to so Kc double primes is equal to the square root of Kc. So the Kc primes is equal to the square root of Kc. So we can get this value. Okay, the unit of the concentration for the condensed base in the mole per liter or in atm. So Kp is equal to RT change in number of mole of the gas of the products minus 2 moles of the reactant times to Kc, which is Kp is not equal to Kc, and Kp and Kc is dimensional quantity. Okay, the specify the balance equations and temperature when quoting a value for the equilibrium constant. And if the reaction can be expressed as a sum of the two or more reactions, then the equilibrium constant for the overall reactions is given by the products of the equilibrium constant for the individual reactions. What is the relationship between chemical kinetics and equilibrium constants? Reversible reactions occur via mechanical consisting consisting a single elementary step. For example, reactions between 1 mole A and 2 mole B producing AB. Forward rate F, subscript F, is equal to Kf, concentration AB. Okay, and for reverse rate R is equal to Kr, constant R for reverse reactions is equal to KRAB. Okay, and then at the equilibrium change, which is Kc is equal to Kf over Kr. Okay, so the rate constant are temperature dependence, so the equilibrium constants must also change with the temperature. Okay, similarly for more than one elementary step. For the step 1, so the rate for forward reactions is equal to Kf, and rate for reverse reaction is equal to K reverse B2. While for the second step, rate for forward is equal to K double prime F A B, while for rate for reverse is equal to K double prime R A B. So means that the overall reactions is equal to the summations of step 1 and step 2. So we can cancel here. So we get A plus 2B producing AB2. So means that the K prime for the step 1 is equal to rate for forward divided by rate for reverse for the step 1 reactions, and for K double primes is equal to rate for K double prime forward divided by rate double prime reverse. So Kc is equal to K single prime multiplied by K double prime. So we can get these equations. Okay.